Hi. Like the other speakers, I would very much thank you to attend, and I hope you enjoyed the shorter BR lines this afternoon. So, as my title says, it's different what everybody else presented here. It's about Southern California, so it's an active tectonic zones. And I would like to acknowledge here all my co-workers, which are also all at the Lawrence Berkeley lab. Thank you. I'm on the back, sorry. Wrong keyboard.
Not this one.
Yeah. No, it's this one.
This one, okay.
So I will talk about potential induced seismicity from wastewater disposal in the Southern California. I will present quickly why the Southern California is different. Closer to mic? Okay. And so I will show analysis on a basin level for Southern California, so different tectonic basin, different oil reservoirs in Southern California. We'll go over the recording completeness, the p-value distribution, and I will show some statistics there. So if you've been to any talk involving induced seismicity, I'm sure you have seen this talk before. As we can see from the outturn here on a Friday afternoon at HEU, there's definitely increased the attention to the induced seismicity. And there have been several large events which have been discussed here a lot, and they're all here in Oklahoma or in other areas. And most of them, they're not directly related to the hydrofracking, but the wastewater disposal wells that are connected to that. And this figure here is from a picture by Bill Ellsworth. And what we need to see here, it's cut off. California is not part of it. So besides two posters this morning in the poster session, which I hope you all attended, there hasn't been really any study of induced seismicity in California. And of course, it's more difficult there because in Oklahoma, there's no seismicity, and then the seismicity after water disposal wells were active, so it's much easier to say a correlation. And the most induced seismicity that you have seen in California was related to geothermal wells. Like you have seen several talks about geysers. I think this time there was no talks about COSO, but other HEU and other conferences, there's lots of talks about the COSO geothermal field. And there's more geothermal fields, which I didn't mention here. And just as a reminder, I don't think I need that in this session specifically, but induced events can go relatively high ups. To date, the largest one was in Prague, Oklahoma, 5.7. So why is Southern California different? Southern California is a highly active tectonic area. These are all the stretch measurements from different studies. This is just a sample of large magnitudes events. So Kern Country in 1915, Landers, which has been studied a lot. The Northridge earthquake, which has been studied a lot, and there's tons more. This is just a snapshot. And here is just all the seismicity above magnitude 2, color-coded, and the circle size scaled by magnitudes. So we see here lots of magnitudes larger than 6. We have LA here, which is a highly populated area, so it's an active zone. And then what we have Southern California has many, many oil fields, especially here in the San Joaquin Valley. This is the Santa Maria Valley, this is the Ventura Basin. And this, related to these oil fields, the active water disposal wells. On this plot alone, there's 1,500 active water disposal wells from the Division of Oil and Gas and Geothermal Resources, DOGGR for sure, which you might have heard before. And all of those, there's data dating back to 1977, where, not saying that there hasn't been any disposal before that, but there's data since then. And all of them can potentially be related to any injection. So what we've did, this is what I'm presenting here is everything is very much work in process, and it's preliminary results. So we looked at the completeness, which is very important. As you've seen, most of the induced seismicity is microseismicity, so it's below 2. It's sometimes even negative magnitudes. We did a short p-value analysis, which we have to extend, but I will present some results here. And we looked at the nearest distances between events to find clusters. So here first is a completeness map of the whole state of California. The blue areas are not necessarily worse, it's just limited just to the active areas here. And the scale goes from 0.5 to 2.5, and what you can see here, we are somewhere up here. The most thing that you can see here, the Central Valley is bad. So the darker the colors, the worse it is. And all the hotspots here, the yellow ones, are basically active areas. There are lots of stations. If you have more stations, basically you have a better completeness. So here, this is Mammoth Lakes, where it's an active volcanic area. This is Parkville, where you have lots of stations. And so it varies a lot. And we did this basin by basin analysis. Here I'm showing you one for San Joaquin and one for Santa Maria. And the completeness there would be there where sorry, I'm away from the microphone again. For those of you which are not familiar with plots like this, it's a frequency plotted against the magnitude. And the linear area is supposed to be described with the Gutenberg-Richter law, which is log n minus a. Log n is equal to a minus b times m, and b is the slope of this linear area. And where it diverges from that, that's down to where the catalog is supposed to be complete. What we can see here, for the San Joaquin Valley, you see a huge discrepancy, and what we find is if you just take the whole basin, it's much too general. So what we did then, we did it on a much smaller scale, basin by basin. So for those of you which are not familiar with South California, this is the San Joaquin Basin. Bakersfield is somewhere down here. All the triangles, which I hope you can see, are the active water disposal wells, which were plotted before in orange. So it's the San Joaquin Basin, the Santa Maria Basin, the Ventura Basin, and the LA Basin, and the relatively small Cuyuma Basin. And this is the completeness based by level, by basin. It's the same color scale. You can see here it's better, but then here the dark blue is relatively bad. In LA and Santa Maria, it's all around 1.5, so it's not great, but it's okay. And if you looked at, so the mean is all more or less close by, but we see here, especially in San Joaquin, there's areas where we cannot detect magnitudes below 3.5, which if you have induced seismicity around there, it's most likely below 3.5. What we did then as well, p-value analysis on the basin level. And just like this, it looks like there's lots of variations. The color scale is from 0.5 to 1.5, and overlaying are again the wells. And this needs much more analysis, which we can't present here in this topic because it could be a talk by itself. But I'm just showing you here the example of the Ventura Basin. On the left here, I'm showing all the magnitudes, all the b-values below the mean. The mean is around 1.1, and on the right side here is, sorry, those are all the ones above the mean b-value. Those are all the ones below the mean b-value. And if you can see here, again, those are the wells. There's some correlation that it could be that the higher b-values are more correlated with the wells, but we need more time to look at the well-by-well analysis. And this is just a snapshot over the whole time. So it's in the catalog from '84 until 2013. So we need a temporal evolution. And what you can see here, all the low b-values, this is all the Northridge aftershocks, which in the future we probably have to take out of the analysis because you have wells in here as well, but it's clearly dominated by the Northridge events. So yeah, the most large-scale variations are mainly due to the tectonic processes, which we didn't go into detail here. And the relationship between the well locations and p-values is less straightforward. And so more detailed analysis needed. And as I mentioned, recording completeness is not very good, so which might bias this analysis. If you don't have enough of the small events, the slope of the Gutenberg Richter will be biased. And which means if you look at any induced seismicities work, most of them, they have local network which are just determined to record those events. But if you base this whole analysis on not on a local network, but on a regional network, you will miss much of the tiny events. And here, some of the statistical analysis we did is to find clusters. We calculated the nearest neighbors on a basin level. And here, this is presented based on the Santa Maria Basin. So this is the whole Santa Maria Basin. And those are all the events in the catalog. And you can just about see the wells. And the color scale is what are the closest events to this event. And we focus on this cluster here, highlighted in the red square, which is shown here. Those are all events which happened between about 84 and then 87. And there's several wells here. We will show the data, the injection parameters from those highlighted wells. So we look if we find any correlation between the injection history and the seismic history. I hope you can see the colors. I hope it's not too blurred out. So this is the time scale. It starts in 83 and goes down to 99. We have this one cluster in 84, and we have this other cluster in late 87. And if you look at the dark blue well here, which was the one in the middle here, you see it starts injection here shortly before this cluster starts. For the second cluster, we have the dark green well, which changes the injection regime here, which could be a correlation, but it could also be no correlation before we have this second cluster. And then we also looked at the pressure history, which is reported as well. And again, for the first cluster we have here, you saw the injection did not increase that much, but then the injection pressure increased much more. So you had, in the green well, you had more injection, but here you have the pressure history, the pressure injection, which is much higher. For the second cluster, we don't really see any correlation if you look at it. But then what you see here is this well, and this well, they all have plateaus for over half a year. So we figured that this is probably a reporting error, that there was something that was not reported. It's just exactly the same value. And then you suddenly have this low here and this high here. So it might very well be that in the injection history there's something happened there. So we could find the correlation there as well. So I'm coming to the summary and conclusions. So it's not a straightforward process. That's why there's not much presented here about it, because it's not, you can't go there and say, hey, we have seismicity here, we have a well here, this must be correlated somehow. But you have seismicity here, you have a well here, and you have tons of faults there. So it's a much more detective work to find something. All that we showed here, it's not statistically significant. It's all just, it could be, it could not be. It needs much more in-depth work to find if it's anything, if it's just randomly a cluster that happened at the same time or not. And as I mentioned, the high recording completeness makes it much more challenging, and we need more well-by-well analysis. And the timing, it's not sufficient for significant results, but it could be explained by a random process, it could be correlated. But it's important if the well injection will be, what we saw in Oklahoma, all the induced seismicity started after the injection was picked up. If we do that in SoCal as well, it will pick up as well. So we need to understand the relationships. With that, I will close and thank you all again.